Assalamualaikum and hi everyone. My name is Siti Fatim binti Rosli. Together with my partner Tarshini, we'll be presenting about the application of atomic absorption spectroscopy in environmental analysis. So both of us decided to talk about the determination of trace metal in water and sediment sample from Ismaelia Canal using atomic absorption spectroscopy. So what are trace metal and where do they come from? Okay, trace metal are elements such as ferrum, manganese, cadmium, nickel, copper, lead and cobalt that normally occur at very low levels in the environment. Usually, living things need a very small amount of some trace metal, but high level of these metals can be toxic. Trace metal are usually released through human activities such as mining, burning of coal and wastewater disposal. It is often difficult to determine how toxic a trace metal is. The toxicity depends not only on the level of the trace metal in the environment, but also where it is found in the environment, such as in water, soil, or sediments. The determination of the concentration of trace metal in the environment usually are difficult and often vary according to techniques. But by using correct analytical techniques such as atomic absorption spectroscopy, the determination of trace metal can be performed as it provides short analysis time and low cost. So let's move on to the type of sample and sample preparation. Here we have two types of sample, which are sediments and also water. I will explain the sampling process for each of the samples, starting with the sediments. So here we have 6 sediments which are collected from different places around the Egyptian Atomic Energy Authority. It comes from lake and also factory. The samples were collected by cutting a V-shaped slice. A knife is used to cut the center portion of the sample, which then placed into a clean bag. For the sediments, we need to preserve them by air drying method. Why we need to do so? Because it can reduce the rate of the possible reaction in the soil sample. For a sediment sample, we have a digestion process where portions of 250 mg of different sediments were digested with 5 ml of hydrofluoric acid, 5 ml of nitric acid and also 1.5 ml of perchloric acid. The aliquots were taken up in 1 ml hydrochloric acid and filled up until 50 ml with the ionized water. So next we will look at the sampling of water. The sampling process begins with collecting 7 water samples from different places around the Egyptian Atomic Energy Authority. The sampling bottle, which made up of polyethylene, were cleaned with 25% of aqua regia for 24 hours and then rinsed with the ionized water and filled with 1% nitric acid. After that, the bottle will be stored in individual plastic bags. At the sampling sites, the acid will be removed and the bottles will be rinsed 3 times with sample prior to filling, capping and being returned to the plastic bag. The water samples were taken at a depth of 1 meter using an acid clean bottle. The pH value of each water sample were measured with pH meter range between 8.3 and 8.57. In the laboratory, 5 ml of each water sample were acidified by 1 ml of concentrated nitric acid, and then they will be heated to 70 degrees C for 3 minutes and being transferred to 100 ml volumetric flask, and then diluted to the mark and were filtered through 0.45 micrometer filter and then will be stored in a refrigerator until analysis. Next, moving on to the third part, which is selected instrument with justification. In this study, the analysis of ferrum, manganese, cadmium, nickel, copper, lead and cobalt were carried out using atomic absorption spectroscopy AAS Vario 6 from Germany, which operates in 2 modes, a single beam and double beam. So the diagram shows a single beam atomic absorption spectrometer. What is actually a single beam photometer means? So it is called a single beam because all the measurements are based on the varying intensity of a single beam light in a single optical path. Why we choose a single beam mode? This is because a single configuration has fewer components and is less complicated. Therefore, it is easier to construct and less expensive than other types of photometers. With a single light path and a minimum number of optical components, a single beam system typically provides a very high light throughput. Next, we are moving on to the double beam mode. So as you guys can see, this is a figure of a double beam atomic absorption spectrometer. So why they are called as a double beam? Basically, they use additional optics to divide light from the lamp into a sample beam and reference beam. So in the double beam system, the reference beam serves as a monitor of the lamp intensity and the response characteristics of common electronic circuitry. Therefore, the observed absorbance determined from a ratio of sample beam and reference beam readings is more free of effects due to drifting lamp intensity and other electronic anomalies which similarly affect both sample and reference beams. A double beam technology which automatically compensates for source and common electronics drift allow this instrument to change lamps and begin an analysis immediately with little or no lamp warm-up for most elements. So this is not only reduced analysis time but also prolongs lamp life since lamp warm-up time is eliminated. In this analysis, a double beam system which uses a beam splitter to generate sample and reference beam may use 75% of the source emission for the sample measurement and only 25% for the reference measurement. So using such techniques, double beam instruments offer virtually the same signal to noise ratio as single beam system while enjoying the high speed automation benefits and operational simplicity of double beam operations. So that's all from me. I will pass the presentation to Tarshini.
Now I'm going to talk about the instrumental parameters. For this particular study that involves the quantification of ferrum, manganese, nickel, copper, cadmium, lead and cobalt, AAS, as stated in the slide, which is the Vario 6 analytical journal from Germany, was used. So this particular instrument is compact and fully automated for single element as well as multi-element analysis that basically makes it suitable for this trace heavy metal analysis. It also operates in two modes which are single beam and double beam. In general, this instrument typically requires around 2 to 5 ml of sample. Next is the wavelength. The wavelength of each element of our interest need to be adjusted as shown in the table. It is also important to adjust the slit width that actually alters the instrumental bandwidth. The slit width should be kept as narrow as possible, but need to make sure that the slit is sufficient enough to allow the radiant power to reach the detector. So it basically shouldn't be too wide and it cannot be too narrow as well. If it is too wide means it will allow multiple wavelengths to pass through, which might result in poor resolution even when the signal to ratio is good enough. Next, on the other hand, if it is too narrow means it will lead to a better resolution, but the amount of light that reaches the detector will be lesser, which eventually will become difficult to detect our analyte. So in this case, all the slit width was kept at 0.2 nanometer, except for cadmium and lead, which was kept at 1.2 nanometer. Next, talking about the flame, for all the elements, acetylene, the mixture of acetylene and air flame was used mainly due to the temperature concern. The temperature for this acetylene air mixture is high and sufficient enough to break down the element molecules to ground state atoms, which is very important for the initial stage of our analysis using AAS. And even during this time, the sample will be inside the flame as well. So the molecules, the ability to reduce the molecules to the ground state by using this acetylene air is the main concern for the selection of this combination. So this mixture of acetylene and air flame provides the temperature that ranges between 2200 to 2400 degrees Celsius. That is the most favorable condition for the dissociation of molecules. Next, I will also touch a bit on the result and discussion part for this study. So the graphs here shows the calibration curve for the heavy metal solutions that were manually prepared, and the calibration curve were plotted with the absorbance against the concentration. Next, this table here shows the detection limit of heavy metal by using AAS, and the graphs below shows the difference between the concentration of heavy metal detected in the water and sedimental samples by using both ion chromatography as well as AAS. Moving on to the interference part, interference is generally any effect that alters the signal while the analyte concentration is kept at a constant level. So in this study particularly, the usage of AAS can be considered as an advantage due to its limited interference, especially for this trace heavy metal analysis, and that is the reason why in most of the environmental analysis, AAS have been chosen as the analytical instrument. So those interference which might have occurred during this water and sediment testing are easily controlled and might be the reason behind the difference in the concentration detected by ion chromatography and AAS for the water and sediments, as shown in the graph earlier. So in this field of water analysis, most commonly encountered interference are chemical and ionization interference, but the ionization interference is mostly limited to group 1 and group 2 elements. Other type of interference are, which is the less commonly encountered one, will be the non-atomic absorption and also the matrix interference. So let's look into each of these interference in detail. Firstly, let me explain about the chemical interference. Chemical interference will usually happen when the element of our interest chemically combines with another reactive component inside the sample. So this combination will actually alter the number of free atoms available to absorb the light, meaning the analyte is not totally decomposed inside the flame. So in other words, we can also say that it actually affects the atomization process of our analysis. Therefore, this scenario can actually reduces the absorbance of the analyte, which might give rise to the inaccurate reading. So chemical interference can be controlled in two ways. The first one is by the addition of releasing agent. A releasing agent is a chemical which actually which will react with the interfering component. So it is basically a cation that reacts with another that will react with the interfering anion and makes the element of interest freely available. Alternatively, we can also use a higher temperature flame. This is because more energy is available to break down the compounds, which would be stable in cooler flames. Moving on to the next interference, which is the metric interference. This interference might have occurred due to the difference in the viscosity and surface tension of the sample and standard. This interference mainly occurs when the sample matrix is so complex that the viscosity, surface tension, and the components cannot be accurately matched with the standard. This actually affects the overall uptake rate, nebulization efficiency, and the atomization processes in the flame. So matrix interference may be controlled by the use of addition technique by changing the instrumental setting, adjusting the fuel to oxidant ratio in flame, use the different oxidant for flame, increase the temperature of flame, and finally use a blank to zero the instrument can also be a good suggestion for this matrix interference. For scattering, from what you can see there, the scattering might happen due to two major causes. The first one is the scattering of radiation source due to matrix purities. Sometimes this scenario might also happen due to the incomplete combustion of organic material. So in order to avoid scattering, the absorption and the scattering of radiation by flame atomization can be corrected by analyzing a blank. The final interference that I'm going to discuss is the spectral interference, which is caused by radiation overlap of absorption line due to the emission from another element or compound, and this usually can be from the flame, solvent or sample. So the prevention that can be taken to avoid spectral interference are the use of alternate wavelength, smaller slit width to limit the wavelength, and also the usage of blank.